How can FTIR be used to characterize surface coatings? Why use infrared spectroscopy? FTIR stands for Fourier Transform Infrared Spectroscopy, a widely used method of infrared spectroscopy. Infrared spectroscopy, or IR spectroscopy, involves IR radiation being passed through a sample, of which some is absorbed by the sample, while some of it is passed through the sample or transmitted. Consequently, the IR spectrum obtained is a representation of the molecular absorption and transmission of the sample, effectively creating a molecular fingerprint. The IR spectrum of a sample indicates absorption peaks which correspond to the frequencies of vibrations between the bonds of the atom which make up the material. Furthermore, the size of the absorption peaks correlates to the quantity of material present in the sample under analysis. As every material or sample is made up of a unique combination of atoms, unique molecular structures do not produce the same infrared spectrum. Therefore, IR spectroscopy can be utilized for the purposes of identification and structure analysis as well as qualitative assessment of materials.
FTIR for the characterization of surfaces. The synthesis of surface coatings involves a complex mixture of organic and inorganic chemical compounds. Coatings are of a high significance when deposited on the surfaces of common materials such as metals, ceramics, and polymers, as they allow for new functions of the material such as anti-corrosive, reflexive, sensory properties, and more. The properties of the coating are dependent on the chemical structure of their formulation. FTIR can be used in the characterization of these surface coatings by assessing the functional groups present. Why FTIR? The original infrared instruments were dispersive spectrometers. In these instruments, using a prism or grating, the individual frequencies of energy emitted from the infrared source are separated. A detector is then able to measure the amount of energy at each frequency which has passed through the sample, forming a spectrum of intensity versus frequency. Over the years, many advances have been made in IR spectroscopy. One such example is the development of FTIR.
The measurement of individual IR frequencies by these dispersive spectrometers results in a slow scanning process. However, FTIR allows these IR frequencies to be measured simultaneously using what is known as an interferometer, therefore reducing the scanning time. The interferometer utilizes a beam splitter which divides the incoming IR radiation from the source into two optical beams respectively. One of these beams is reflected off of a mirror which is fixed in place. The other beam, however, is reflected off of a mirror which is able to move a short distance from the beam splitter. After both beams are reflected, they are recombined when they meet back at the beam splitter. As the path followed by one beam is fixed while that of the other is constantly changing due to the moving mirror, there is interference between the two beams. This resulting signal is known as an interferogram, which contains information about every IR frequency originating from the source. Effectively, what this means is that as the interferogram is measured, all the frequencies of IR radiation are measured simultaneously. To interpret the signal, the mathematical technique of Fourier transformation is applied, which transforms the interferogram into a frequency spectrum which can be used for analysis of the material.
Instrumentation. How is a sample analyzed? IR radiation is emitted from the source. This beam passes through an aperture towards the sample. The beam then enters the interferometer, spectral coding occurs, and an interferogram is produced. The beam enters the sample compartment where it is absorbed or transmitted through. Specific frequencies of energies which are uniquely characteristic of the sample are absorbed. Finally, the beam passes to the detector for final measurement of the interferogram signal. The measured interferogram signal is processed by the computer and Fourier transformation occurs. Hence, the final IR spectrum is generated for analysis.
Applications. A common example of FTIR being applied in the analysis of surface coatings is in the development and production of paint. FTIR can be used to identify between different commercial paints on the basis of the different functional groups present in the respective formulations. It can therefore assess the effect of degradation due to environmental exposure. Polymer films. Polypropylene is commonly used in manufacturing as it infers useful chemical and physical properties such as hydrophobicity, mechanical strength, thermal insulating capabilities, etc. The use of polypropylene as a surface coating, however, has been found to have weak molecular interactions with the material itself, which can be combated by creating new functional groups on the surface using chemical, electrochemical, and physical methods. FTIR spectroscopy can be used to characterize the polypropylene films with their modifications and assess the effectiveness of the method of synthesis. A vast majority of surface coatings are prepared from polymers, hence this process of characterization by FTIR is widely used. In summary, in comparison to previous IR techniques, the advantages of FTIR include the faster scanning process, increased sensitivity and resolution due to more sensitive detectors which reduce noise, as well as the mechanical simplicity of the instrumentation and no need for external calibration. Hence, FTIR is a reliable technique for the characterization of surface coatings by assessing the functional groups present.